Hi folks, welcome to Maths and Physics for You. Nice to be back with you after some time. Today we're going to talk about eigenvalues and eigenvectors. These are very important topics in engineering that you will encounter them, especially in mechanical as well as in structural engineering. Okay, now let's see, we have the following equation. This is a transformation equation that involves a transformation matrix. We have a vector x. X here is a vector, so it's subject to transformation, and the result of the transformation is x multiplied by a scalar. So there is a relationship here. Even though we have a matrix multiplied by the vector x, we get another vector that is a multiple of the original vector x. So it could be like increase in length, or could be decrease, or could be change in direction. That is dilation or contraction. So lambda here is called the eigenvalue of matrix A. The eigenvalue. Eigen comes from the German language, which means proper. Eigenvalue, proper value, or characteristic value of A, because it shows you by how much the vector x has contracted or dilated. Okay, but it has to keep the same direction for this to hold, because these two vectors, they must have the same direction. Anyway, it's x, and this is a multiple of x, because lambda is a scalar. So eigenvalue is a scalar. It's a number multiplied by x. And A is the transformation matrix that defines the transformation operation, and x is called now here the eigenvector of the matrix A, but this corresponds to the eigenvalue. So that's how they are related to each other. So this is the equation Ax equals lambda x. This is the equation that defines the transformation process, and that helps us to find the vector, the eigenvector, and the eigenvalues as well, and we can see its applications and verify it. As we can see from here, this involves a matrix on this side, but on this side we have only a scalar. So that they are equal, similar, we introduce a matrix, the identity matrix. I is the identity matrix. It's like when you multiply a number by 1, you get the same number, no change. Like 2 times 1 is the same like 2. So we have here, we introduce the identity matrix, which is, as we know, it's given by 1, 0, 0, 1. So this equation 1 here can be rewritten like this: Ax lambda Ix. So we put I, the identity matrix, so that we have a matrix here as well as matrix here. So Ax equals lambda Ix. Now simple rearrangement and operation, as x, this comes to this side, so, and the x at the outside as common factor, so we get A minus lambda I. A, this comes to this, minus lambda I equals to, multiplied by x equals to 0. This is a linear equation from previous lessons. This is a homogeneous, called linear equations, and we're testing for a homogeneous equation has been done before in the previous lessons. And also by Kramer's theorem, for the solution for this to be non-zero solution, we are interested when we are after solving this to find x. This is our point. we need to find the value of x, the vector, the eigenvector, the value of x. That's what we want. Of course, if you put 0 here, that satisfies the solution. X equals 0, of course, that will give you equal to 0, but this is not useful. In mathematics and engineering, we are not interested in that. This is trivial solution, not interested in that. We want the non-zero solution, the non-trivial solution, they call it. And so by Cramer's theorem, that's obtained, that must be the determinant of the matrix A minus lambda I. This is a matrix. A minus lambda I is a matrix. Its determinant must be equal to 0 for the solution to hold. So this is the important equation here, the most important equation that we will use, and we use to find the values of lambda, the eigenvalues. And that's what we do in the following example. Okay, folks, now to clarify this concept of eigenvectors and eigenvalues, we're going to solve a problem. We have an example here. So we are given a matrix A, as we can see here, 3, 2, minus 1, 0. This is 2 by 2 matrix. And we are required to find the eigenvalues, the proper values of this matrix. And after that, we will find the corresponding eigenvectors. And we will verify, after we find the vectors, how it means physically. What does it mean? The dilation or contraction of a factor by these factors, which are called eigenvalues. Okay, so let's start with this, finding the eigenvalues. As we saw before, these are the most important equations that we need. We need to use this one, which these two lines means the determinant. This stands for the determinant of the matrix A minus lambda I must be equal to 0, as we said. So all we have to do is to substitute the values of the matrix A minus lambda multiplied by I, the identity matrix, as we can see, 1, 0, 0, 1 equals to 0. A simple substitution will get 3, 2 minus 1, 0, and this one is expanded, so it's lambda 0, 0, lambda. Becomes, as we can see here, this must be equal to 0. Again, we're subtracting, so 3 minus lambda, 2 minus 0, minus 1, and 0 minus lambda is minus lambda, so this must be equal to 0. As we know, this is determinant, so it's like a cross multiplication. This times that minus the diagonals, minus 1 times 2. So we have minus lambda times 3 minus lambda minus 1 times 2. So as if it is a cross multiplication, but with the minus there. And simple process here, simplification, we get this equation, lambda square minus 3 lambda plus 2 equals to 0. This is the characteristic equation. This is, they call it characteristic equation of matrix A. So we solve it by factorization. So you got lambda minus 1 into lambda minus 2. So you got plus 2, so minus 1 minus 2. And that gives you the solution. Lambda equals 1 and lambda equals 2. So these are the eigenvalues of A. These are the dilation or contraction values of A. Obviously here, because they are positive, plus 1, plus 2, it means dilation. And vector x will continue to have the same direction because the value of lambda is positive. Okay, now after we found the eigenvalues, we want to find the eigenvectors that corresponds to them and verify the solutions and to see what they represent. Okay, so we found two values, lambda equals 1 and we have lambda equal 2 corresponding to the matrix as we started, transformation matrix A 3 2 minus 1 0. Okay, so we are here to find the eigenvectors corresponding to these two values. So we have lambda equals 1, and again we do that for the same thing for lambda equals 2. So the same steps we follow for each. Okay, so the vector x, we assume that it's AB. It's AB. This is because A, the matrix A is a 2 by 2 matrix, so it has only two coordinates, A and B. So we apply the equation here, equation 1, AX equals lambda x. We know A given 3 2 minus 1 0 multiplied by vector AB equals to lambda, here we have 1 AB. As we can see, we can look at both at the same time because they are similar. We have lambda equal 2 here, so here the same thing on the left hand side. On the right hand side we only substituted 2 instead of 1, AB. Okay, so following simplification of matrices, this becomes 3A plus 2B equals to 1 times A, and also minus 1 times A plus 0 times B, that's here, the second row, equals to B. So if we solve these two equations, any one of these, both of them, they will give you the same answer. That is B equals minus A. And this one, B equals minus A. Alright, we are after X. We want X, the eigenvector. So X is AB. Okay, in terms we use A, so it's in terms of A, but B equals to minus A, so we sub it here, minus A. So A is common, we take it outside, so X is equal to A, remaining 1 minus 1, 1 minus 1. So this is the first eigenvector, or eigenvector corresponding to lambda equals 1. So x equals a1 minus 1. So this is a series of solutions that corresponds to various values of a. So it could be a equals 1. This is satisfied. If we have x equals 1 minus 1, is satisfied. If a is 2, that is 2 minus 2, is also satisfied, and so on. This is, in geometry, you can represent it on these axes. So if assuming a is 1, so x will be 1 minus 1. This is x is 1, its coordinates, and minus 1. So it looks like this. And if you substitute this value, 1 minus 1, if a is 1, in the original equation here, and this is left for you as simple exercise, it will be satisfied. We put lambda equal 1, substitute the left hand side, right hand side, it will give you 1 minus 1. So this means that after this operation we get the same vector. So there is nothing happening here. The transformation resulted in no change in the vector. This is because lambda equals 1. So there is no contraction, there is no dilation. So this is what it means. So if you draw the vector as a result of the transformation, it's exactly the same vector, coincides together. But with the second one, lambda equals 2, let's see what happens. Similar situation, we sub the values, you got here as before, 3a plus 2b, 3a plus 2b, but now we have 2a. And the second row will give you minus a equals 2b. Solving any of these two equations will give you b equals minus half a. So this means x, the vector, equals ab equals a minus half a. A is taken outside, so 1 minus half. So again, this is a series of solutions for various values of a. Again, we can verify by putting a equals to 1 and subbing in equation 1. We sub a, which we know what is a, x, our new value, 1 minus half, because we assume that this a is 1, lambda is 2, x is 1 minus half. If we do that, as we can see here, this is quickly and briefly, are they equal? After simplification, the answer is given, yes, 2 minus 1 on the left hand side and 2 minus 1 on the right hand side. And this is equals to 2x, because we said a is 1, so x is 1 half. So this is double. This transformation on the right hand side, a times x, has resulted in a new vector that is double the length of the original vector. It is double 2 times, because lambda equals to 2. So as you can see here, that lambda represents the magnification factor, the dilation factor, and resulted in a vector double the size, and in the same direction, because we have plus 2. Thank you for watching, and please subscribe. See you in the next videos.